Unit 2, Section 6. Today we're going to be talking about solving absolute value inequalities. So this brings back absolute values into our equations. If you remember from Unit 1, when we solved equations with absolute values, we always had two solutions. We had two cases. We had the positive case and the negative case. And that's going to be true when we're solving absolute value inequalities as well. So let's take a look at our two key concepts for today here. Our first key concept, which we call case 1 here, is when our absolute value is less than a positive number. Remember, absolute value represents distance between that expression inside and 0. This says the distance between x and 0 is less than 2. Well, this is an AND statement. Whenever you have the absolute value less than a positive number, this is going to represent an AND or an intersection or the overlap. All right, so if we were to graph this on a number line, we're going to put our 1, 2, 3 on that side and got -1, -2, -3 on the left side. We want all the values here that are going to be between -2 and +2. All right, because remember, we're taking the absolute value of this, and so if I put -1 in, took the absolute value of -1, that will be less than 2. All right, our second key concept, which we call case number 2, is when our absolute value is greater than a positive number. Well, this is going to represent an OR case. All right, so this means our distance between x and 0 is greater than 2. All right, so if we are to number our number line here again, just like we had above, then we are going to graph an open circle here at 2 and everything to the right, or we're going to graph here an open circle at -2 and everything to the left. Again, if you were to take, let's say, for example, -4 and substitute it in here for x, the absolute value of -4 is greater than 2. This is a true statement because the absolute value of -4 is +4. So whenever you see an absolute value that's less than a positive number, keep in mind this is going to look like an AND statement. And whenever you see an absolute value or greater than a positive number, this will take on the form of an OR statement. All right, let's jump into some examples here, and I think you'll see what we mean. Solve each inequality, then graph the solution set if possible. Notice that these two examples, A and B, are both case number 1. Where we have an absolute value that is less than a positive number. I'm just going to jot that down up here. All right, so we're going to create AND statements here. All right, our absolute value is isolated, and we're going to create our two cases. M plus 3 is less than or equal to 2. There's our positive case. Now, when we create the negative case, we need to reverse the inequality symbol. We have m plus 3 is greater than or equal to -2. And there's our negative case. All right, solving both of these, we're going to subtract 3. M is less than or equal to -1. And, because this is an AND statement, we're going to subtract 3 over. We have m is greater than or equal to -5. All right, so if we're going to plot these on our number line, we got -5, -4, -3, -2, -1, 0, 1, and 2. We want all of the m's less than or equal to -1. So here's a closed circle at -1. And all the m's greater than or equal to -5. So it's going to go all the way over here to -5 with a closed circle at -5. And everything in between will be a solution to this inequality. All right, let's take a look at example B. Example B, we have an absolute value of 3c minus 5 is less than -2. Uh-oh, we got a little bit of a red flag here. What do we notice on the right side of that inequality? We have an absolute value that is less than a negative number. Now remember, absolute value can never be negative. It's always a positive value. Well, you can never have a positive value that's less than a negative number. So right away, in this case, we notice that there is going to be no solution. And we don't have to go any further in order to solve that absolute value inequality. All right, in example 2, we're asked to solve each inequality, and notice that here it says case number 2. In case number 2, we were talking about solving OR statements. All right, so we have an absolute value, x plus 3/8 is greater than or equal to 2/3. It's already isolated, so we don't need to do anything here. We're going to create our two cases. The positive case, so x plus 3/8 is greater than or equal to 2/3, or x plus, let's try that again, x plus 3/8. And now remember, we got to change the direction of inequality and make our negative case is less than or equal to negative 2/3. All right, so let's solve both of these. We're going to subtract 3/8 over, and that's going to leave us with x is greater than or equal to 2/3 minus 3/8. We need to change those denominators so that they have common denominators. Is going to be x is greater than or equal to 1/40th, and then we're going to subtract our 3/8 over on the other equation, and that leaves us with x is less than or equal to negative 2/3 minus 3/8 is going to give us negative 31/40. All right, so we got some very strange looking fractions here, but remember this is an OR statement, and we'll go ahead and graph these now. So here's 0, we're going to put 1 way out here, negative 1 way out here. Well, 1/40th is very, very close to 0. We want all of those x's greater than or equal to 1/40th, so that's everything shaded out here to the right, or all of the x's less than or equal to negative 31/40th, which is pretty close to negative 0.75. So we're going to put that circle there and everything shaded to the left. All right, so there's the graph of that solution set to that absolute value inequality. Let's try our next one here. We have the absolute value of 12 plus w is greater than or equal to negative 5. Once again, you see there's a negative that pops up in this absolute value, which remember, absolute value can never be negative. It's always a positive value. And what this statement is saying is a positive value is greater than or equal to a negative number. And this is going to be true always. In other words, no matter what value for w you put in, it's going to create a true statement. And when it's true always, what we're going to say is that there are going to be infinitely many solutions. And when there are infinite solutions, remember this, we're going to color in our entire number line. So we'll create big, thick, dark arrows going off in both directions and a solid line between those arrows. All right, let's take a look at example C, which gets a little bit more complicated. Now you'll notice that our absolute value is not isolated. And remember, that's our first step. Isolate that absolute value. Oops. All right, so we're going to first start by moving over the 5 by addition. We'll add the 5 to both sides, and that gives us 6 times the absolute value of 2x plus 3 is greater than 12. And now we're going to divide both sides by 6. And that gives us the absolute value of 2x plus 3 is greater than 2. All right, we have an absolute value that's greater than a positive number. This is an OR statement. All right, and we're going to create our two cases now, one for our positive case. So 2x plus 3 is greater than 2. Or now we're going to create our negative case. 2x plus 3 is less than negative 2. Remember, you got to reverse that inequality for the negative case. All right, solving straight ahead, we're going to subtract 3. That gives me 2x is greater than negative 1. Divide by 2. X is greater than negative 1/2. Or let's solve the next one here by subtracting 3. That gives us 2x is less than negative 5. Divide over your 2, and you have x is less than negative 5/2, or negative 2.5. All right, so we're going to write this down here. X is less than negative 2.5. When it comes to graphing our inequality, We will put 0 here. Here's negative 1/2. We'll put negative 1, negative 2, and negative 2.5 way out here. So we want all the x's that are less than negative 2.5. That's an open circle and shading to the left. And we want all the x's greater than negative 1/2. So that's an open circle and shading to the right. And there is the graph of our solution set. All right, we're going to pause on example 3 and we'll cover that example in class.